I wanted to do the full relativistic correction to the moving dipole, and the way I'm going to do this is I'm going to define the K prime frame as the rest frame of the dipole. And once again, the dipole moment is going to be parallel to beta, which will simplify some things. But anyway, as before, the electric field, I know the electric field in the rest frame, and that's the starting point. So we're writing that out, so that I now have r prime to the fifth down here, and then just the r prime vectors up here. Now that I have the formula for the electric field in the prime frame, the rest frame, I need to define my coordinates in the moving frame, because this is where I want to write the coordinates. And I'm going to set up my coordinate system with one coordinate parallel to the direction of motion, parallel to beta. And that's going to be my first coordinate. And then my other two coordinates are going to be perpendicular to beta. Now, I also want to write this in terms of spherical coordinates. That where my theta is the angle away from the direction of travel. In other words, the direction, this first coordinate, is the axis for the spherical coordinates. And then my phi is the angle around in the perpendicular direction. And of course, the length of the vectors are. Where the origin is the current position of the dipole. So wherever the dipole is, that's the origin of my coordinates. And so I can write the components of r, right? So this point right here is my vector r, and I can write that in spherical coordinates, which is just a standard going from spherical to Cartesian. And then I can transform my Cartesian coordinates into K prime frame, and since only the first coordinate gets a factor of gamma, the other two remain the same, so that r1 prime is gamma r1, and then the other two are unchanged. I also need the full magnitude of r prime, and of course the magnitude is the square root of the components, sum of the components squared. And then if I write those components in terms of my unprimed components, I can plug in all of this into that formula, and I arrive at a slightly odd formula here by simplifying. Now we have a factor of gamma, but this thing looks almost like 1 over gamma, because gamma is gamma is 1 over square root of 1 minus beta squared. So this looks a bit like 1 over gamma, except for this sine squared theta. And so this is basically the angular dependence, or an angular dependent gamma, in other words. So that if you look at when theta is 0, right, sine of 0 is 0, you just get square root of 1. So that just gives me r times gamma, right, in the parallel to the motion, which is what I expect, because that's the first coordinate. And then perpendicular to the motion, I get pi over 2 for theta. Sine of pi over 2 is 1. So I get square root of 1 minus beta squared, which is 1 over gamma. Which cancels this gamma. I just get r prime equals to r. So r is unchanged in the perpendicular direction, which is what I expect. And so this is just basically angular dependent gamma. So this gives me the electric field in the prime frame in terms of the coordinates in the unprimed frame. But what I'm really after is the unprimed electric field. So I have to transform, right, the E prime into E. The first coordinate does not get changed, opposite to the coordinates for the field, but the other two do. And in almost a happy accident, right, you see that we get a factor of gamma in the 2 and 3 coordinates from the field transformation. And then up here, there's a factor of gamma in the first coordinate from the coordinate transformation. And so basically there ends up 2 gammas in every coordinate, and those can be factored out. So writing the full electric field now, I get this somewhat messy looking thing. And a couple things I'm going to rewrite, right? These 2 factors of gamma can cancel 2 gammas down here. And then I can factor out 2 r's from these r, making these r prime, and that cancels 2 r's down here. And also I can rewrite this p dot r, right, once it becomes p dot r hat, I can write that as the magnitude of p times cosine theta. So just writing down the changes I mentioned here, I get this as the full expression for the electric field in the moving frame. Now I want to know what the magnetic field looks like. And similar to before, I get a beta cross E. Except this time the E is the transformed E. And so there's no other factors of gamma anywhere. And I can just plug this into here. And if I notice that since beta is parallel to P, right, beta cross P is 0, so this factor disappears. And then I just get beta cross R hat. And I can represent that as beta sine theta. And then just multiplying by my theta, or sorry, my phi hat to get my vector back. And so writing that now, I get this for the expression of the magnetic field in the moving frame, which is very similar to what I got before, except now I have gamma cubed and then 1 minus beta squared theta to the 5 halves on the bottom. And so now I want to know, what does this actually look like? I'm going to start by drawing what the dipole field looks like in the rest frame qualitatively. And then ask what happens in 2 cases. So I'm going to look at a plane that cuts straight through the origin where the dipole is at an instant, but is perpendicular to P and beta. And so if I go to my electric field here, this is at theta equals pi over 2. So cosine of pi over 2 is 0. So this doesn't matter. And all I get is this one. Sine of pi over 2 is 1. And so I get, for my electric field, I get minus k. But I notice that 1 minus beta squared to the 3 halves is actually 1 over gamma cubed. Right, because gamma, again, is 1 over square root of 1 minus beta squared, and then I raise it to the power of 3, that's 1 over gamma cubed, and that cancels this right here. And so that just gives me minus kp over r cubed. And so I notice that in this perpendicular plane, that I get something, an expression, that doesn't depend on beta or gamma, right? It's just what it is, no matter what frame you're looking at on this plane. And so qualitatively, these electric field lines stay the same distance from each other, right? They don't get squished at all. And so I'm going to say that this is that perpendicular plane, electric field. Now I also want to look at a line that runs through the axis of the dipole, right? That's also now parallel to theta, and so sine of theta is, so theta is 0. Now if I look on my equation here, I have sine of 0 is 0. So all I get is a 1 here. And same thing for over here, so I get a r cubed gamma cubed on the bottom of both of these. And I also want to notice that P is parallel to r hat here. So I basically just have the vector P here, and I can factor that out from both of those two. And so for that parallel line right there along the axis, for the electric field I get this. 3, minus 1 is just 2, so I get 2p over r cubed gamma cubed. And so I can see that as the velocity approaches the speed of light, gamma gets much bigger than 1, and so this whole thing gets much smaller. And so qualitatively what that means is the electric field lines have to spread out relative to where the dipole is as it approaches the speed of light, because the electric field there is getting weaker. And so if I were to draw what those two effects look like, right, I have along here, those field lines have to be in the same place. So I'll draw where they have to go through. But the field lines out here have to spread out, right? So to keep all that, keep those two effects, right, the dipole has to look something like this. And of course it's symmetric here. Alright, and so what's happening in this picture is basically the dipole is just getting squished. Okay? Just from looking at these two cases, I can tell that that's what's happening. Now I want to know what's happening to the magnetic field. Before, I plotted sine times cosine, right? Because in my formula here, I have the old one only had sine times cosine on the top when at slow velocities, which looks something like this. So the question is, what happens as I approach the speed of light? And you can plot this in a calculator, right? You just add in this factor downstairs, right? Of gamma to the gamma to the third, and then 1 minus beta squared sine squared theta to the 5/2. And basically that extra theta dependence deforms this thing to look something like that. And then as you really get close to the speed of light, it basically becomes an impulse at pi over 2, and the magnetic field is virtually 0 everywhere else. And so in that same, right, as it pancakes, right, in that close to that plane, you get a magnetic field going like that on the one side, and then like that on the other side, and the magnitudes get bigger and bigger right close to that plane. So this is the electric field, and this is the magnetic field around the moving dipole. Oh, and here's the axis. And so there you go.